the electronic configuration of the outermost shell of the element. The periodic table classifies the elements into four blocks: the S block, the P block, the T block, and the outer F block. This table gives us a brief summary of the various groups present in the modern periodic table. These are the 16 groups consisting of 18 columns, and these are the number of various elements present in these groups. The first A and second A group, known as alkali metals and alkaline earth metals respectively, are in the S block. Group third A to 0 group are in the P block. They are also known as boron family, carbon family, nitrogen family, oxygen family, halogen, and inert gases respectively. Boron, carbon, nitrogen, and oxygen are the first elements in their groups and hence the names. Lanthanides and actinides are placed in the third P group, though they are placed outside the main periodic table, but they are counted in the third P group. The groups from fourth P to second B consist of the transition metals. They constitute the D block of elements, in which the eighth group consists of 3 columns, as opposed to the other groups which consist of a single column. This table gives a brief summary of the 7 periods which exist in the modern periodic table and the number of elements in them. The lanthanides are included in 6th period and the actinides in 7th period respectively. And as we can see that the length of the periods vary, that is, they do not contain the same number of elements. As we discussed earlier, the modern form of periodic table has been divided into 4 blocks on the basis of the general outer electronic configuration of the elements. These 4 blocks are the S block, the P block, the D block, and the F block. First of all, let's take up the S block elements. First A group, second A group, hydrogen, and helium constitute the S block. The first A group elements are also called alkali metals because they give alkaline solution on reaction with water. The alkaline earth metals, that is the second A group elements, owe their name to their oxides. These oxides give alkaline solution with water, and their melting points are so high that they remain solid in fires, therefore the name earth. The general outer electronic configuration of first A group elements is Ns1 and of second A group elements and helium is Ns2. Radium and francium are radioactive elements in the S block. The rest are non-radioactive. Hydrogen and helium are gases. Cesium and francium are liquid, whereas the rest are solids. This table shows the alkali metals and alkaline metals along with hydrogen and their atomic number as well as their electronic configurations. As you can see, the first A metals have general electronic configuration Ns1, whereas the general electronic configuration for second A metals is Ns2. The next block is the P block. It is constituted by third A, fourth A, fifth A, sixth A, seventh A, and 0 group elements. The P block elements include metals, non-metals, as well as metalloids. A diagonal is drawn from boron to astatine, which separates the metals from metalloids and non-metals. The P block elements generally show a tendency to form covalent bonds. The general outer electronic configuration varies from Ns2np1 to Ns2np6. There are total 30 elements in this block, of which astatine of group 7th A is radioactive. There are total 9 gases in this block, which are neon, argon, krypton, xenon, radon, fluorine, chlorine, oxygen, and nitrogen. And gallium and bromine are the 2 liquid elements of this block. This table shows the P block elements along with their atomic numbers, which are mentioned in the parenthesis. As you can see, the outermost electronic configuration for third A group elements is Ns2np1. For fourth A it is Ns2np2. For fifth A it is Ns2np3. For sixth A it is Ns2np4. For seventh A it is Ns2np5, and for 0 group elements it is Ns2np6. The diagonal which separates the metals from non-metals in metalloids is drawn from boron to silicon to arsenic to tellurium to STT. The elements on the left-hand side of this diagonal, such as aluminium, gallium, germanium, polonium, bismuth, etc., are metals, whereas those on the right-hand side are non-metals and metalloids. The next is the D block. The general electronic configuration of D block elements is N-1s2, P6, D1 to 10, Ns1 or 2. They are also known as transition elements because, as we can see in their electronic configuration, the ultimate and the penultimate orbits are incomplete. The total elements are 33 in this block till helium, whose atomic number is 105. As new elements are discovered, they are being added to it. Maximum 10 electrons may be filled in a D subshell, and the elements of group 3rd V, 4th V, 5th V, 6th V, 7th V, 8th, 1st V, and 2nd V constitute the D block. Zinc, cadmium, and mercury are not considered typical transition elements since their d orbitals are completely filled. Copper, silver, and gold are also not considered transition elements, or we can say typical transition elements, because the last electron is filled in S subshell. Their electronic configuration is D10NS1. All the elements except mercury are solids. Mercury is liquid. And the main characteristics of D block elements are paramagnetic nature, colored salts, variable valency, and catalytic property. We are going to study these characteristics in detail when we will take up transition metals and coordination chemistry. This table shows the periods involved in the D block and the various elements which constitute it. As you can see, 4th, 5th, 6th, and 7th periods constitute the D block. The elements of the 4th period are also known as 3D series elements because the electrons are gradually filled in the 3D orbitals. As we know that a D subshell can have maximum up to 10 electrons, therefore 10 number of elements are there in each period except the last one. Till helium there are 3 elements, and after that the elements are added as they are discovered in the 7th period. This table shows the electronic configuration of the D block elements. The electrons are filled in d orbitals gradually, and the electronic configuration is as expected till the group 5th V, 3d1 4s2, 3d2 4s2, 3d3 4s2. But in 4th V group in the 3D series, the electronic configuration is 3d5 4s1 instead of the expected configuration, that is 3d4 4s2. It is because of the reason that at this stage the energy difference between the 3d orbitals and the 4s orbitals is very low. So 3d5 4s1 configuration provides extra stability due to half-filled orbitals as compared to 3d4 4s2 configuration. Then the same case happens in the first B group as well. The general electronic configuration of the elements in first B is N-1 D10 NS1 instead of N-1 D9 NS2. It's again because of the same reason that the energy difference between N-1 d orbitals and NS orbitals is very low. And so N-1 D10 NS1 configuration provides extra stability due to the extra stability of half-filled and completely filled orbitals. The same case is followed in 4D and 5D series as well. The last block is the F block, which is placed outside the main periodic table. The F block consists of those elements which have partially filled F orbitals in at least one of their elemental or ionic forms. The general electronic configuration of these elements is N-2 S2P6D10 F1 to 14, N-1 S2P6 D0 to 1 and S2. They have total 28 elements. Now, since We can see from the electronic configuration that their penultimate and pre-penultimate orbits are incomplete. They are also known as inner transition elements. The elements in which 4f orbitals are progressively filled are called lanthanides, and they form the first inner transition series. And the elements in which 5f orbitals are progressively filled are called actinides, and they form the second inner transition series. Lanthanides and actinides are also known as rare earth elements. All the actinides are radioactive in nature. Also, those elements that occur after uranium, that is after atomic number 92 in the second inner transition series, are known as transuranic elements. They are all man-made or synthetic elements. Now let us see what are the advantages of the long form of periodic table or the modern periodic table over the earlier tables. As we pointed out in Mendeleev's periodic table, which followed increasing order of atomic weight, that there were certain elements which were not placed according to the increasing order of atomic weight. For example, potassium, which had higher atomic weight than argon, was placed after it. The same problem was with the pair cobalt and nickel and tellurium and iodine. But since periodic table or modern periodic table follows the increasing order of their atomic numbers, these elements fall well into the place. Another problem with the earlier tables was that certain elements with dissimilar properties were placed together. But in the long form, separate groups were given to such elements. For example, coinage metals, copper, silver, gold were placed separately from zinc, cadmium, and mercury, which showed similarity in properties. Then the diagonal drawn from boron to astatine in the p block separates metals from metalloids and non-metals. The elements which fall right on the diagonal, that is boron, silicon, arsenic, tellurium, and astatine, are called metalloids. Then in a single group, all the elements are going to have the same outer general electronic configuration. But long form of periodic table has its share of defects as well. First of all, position of hydrogen is not clear in this table also, just like the earlier periodic tables. Secondly, helium is an inert gas, but its configuration is Ns2, which is not same as that of the configuration of other inert gases, which is Ns2Np6. Then lanthanides and actinides are placed outside the main periodic table. They do not find their proper place in it. The physical properties of isotopes are different, yet they are placed at the same positions because they have the same atomic numbers. And there are elements with similar properties which are placed in different groups. For example, platinum and gold are placed in separate groups. And similarly, there are some elements with unlike properties but are placed in the same groups. Another important classification of the elements was proposed by the Danish physicist Niels Henrik David Bohr. His classification was based on complete and incomplete electron shells, on the basis of which he classified the elements into 4 groups. First is the inert gases, second is the normal or representative elements, third is the transition elements, and fourth group is the inner transition elements. Inert gases. The elements of the zero group of the modern periodic table constitute this group of inert gases. They are helium, neon, argon, krypton, xenon, and radon. Their outermost electronic configuration is Ns2Np6, but helium is an exception with the outermost configuration Ns2.